It's a beautiful day in this neighborhood, a beautiful day for a neighbor. Would you be mine? Could you be mine? It's a neighborly day in this beauty wood, a neighborly day for a beauty. Would you be mine? Could you be mine? I have always wanted to have a neighbor just like you. I've always wanted to live in a neighborhood with you. So let's make the most of this beautiful day. Since we're together, might as well say, would you be mine? Could you be mine? Won't you be my neighbor? Won't you please? Won't you please? Please won't you be my neighbor?
Good afternoon, everybody. Welcome to Tibbetts Physics. What is crappinin'? Today we are going to look at the hydrogen and mercury energy levels of an atom, and what we'll look at are the energy levels of electrons within that atom. Have you ever looked at a fluorescent light bulb and noticed that when you look at it, you just see white light? And I'll show you a picture right now so you can see what I'm talking about. But if you put on these glasses, what we could do is we could separate that white light into whatever colors make up the color of the fluorescent light. And if we look at the picture now, we could see that we see the colors of the rainbow. And if we recall from earlier that white light is composed of all the colors of the rainbow, and for a fluorescent gas tube, we also see all the colors of the rainbow. But if we were to look at a hydrogen gas tube or a mercury gas tube, we wouldn't see white light, we would see different colors. And if we were to separate it with these glasses, we would also see the specific colors that combine to allow us to see the color that we see with the naked eye. So what we're going to look at today is how do we see those specific colors that create fluorescent light, or the specific colors that make the hydrogen light that we see, as well as the mercury light. Now we can also remember that the light that we see, in order to calculate the color of light, we need to know the frequency, where V equals lambda F. So we can calculate the frequency of the light, and therefore we can determine the color. We learned from the previous video that the energy of a photon, which is essentially light, is based on Planck's constant, h, times the frequency of light. So when we're looking at the colors of the rainbow, when we separate it with these glasses through fluorescent light, the colors that we see are different energies emitted from the fluorescent gas tube. So before we get into how that works, let's revisit Bohr's model of the atom. What we're going to do is draw a model of the atom with, let's say, 2 protons in the nucleus and 2 neutrons. So proton, neutron, neutron, proton. Before we expand outside of the nucleus, let's think about forces. We know that neutrons are neutral, so they don't have a charge, or their net charge is 0. Protons, their net charge is positive 1 e, or positive 1 elementary charge. Since we have 2 protons right here, they're both positive charges, we can recall that positive charges want to repel each other. So there must be something else that's holding these protons inside the nucleus, some other force that's counteracting the electrostatic force, which is preventing the protons from opposing each other. We have another force to learn, and that's called the strong nuclear force. We'll learn more about this force in terms of how it actually works and what causes this force later on. But for the time being, we can say that it's the force that holds protons and neutrons together inside the nucleus. protons and neutrons together inside the nucleus. Okay, and then surrounding the nucleus are the electrons. We know in the first orbital we have 2 electrons, and we learned from Bohr's model atom that the electrons aren't confined in specific orbitals. There's what we call electron clouds, where the electrons can be anywhere around this cloud. And they have a probability of being anywhere at once we measure it. We'll talk more about electron clouds later on, as well as what's really happening with these electrons within their orbitals. What I just said about them having a probability of being in any location is not 100% correct. And also they do have specific clouds or specific shapes of where they can be. Now, we have electrons which have a negative charge and protons which have a positive charge. And we know that these 2 charges are going to attract each other due to the electrostatic force. So we can also say that the electrostatic force holds protons and electrons together. Now you might be asking yourself, well, if the protons are attracting the electrons, why aren't they all getting sucked up into the nucleus due to the electrostatic force or the force of attraction? And this is where quantum physics comes into play. So let's talk about quantum physics and more about the Bohr model, and eventually we'll talk about how we see the color of light when it's emitted from a gas tube. What we're going to do to help us understand these different energies of the electrons, so we're going to make a staircase. So we'll make one going to the left of the screen. And each step is going to get shorter and shorter, so not as high as we get farther along the staircase. So your first step, these are going to be our energy levels of the electron. This first step at the beginning is called the ground state. Oops, let me use a different color. The ground state. And the ground state is when the electron is as close to the nucleus as it can get. For the hydrogen atom, the ground state we call n equals 1. Any state above the ground state, so any step above there, is called an excited state. So anything above the ground state is called excited. Oops, let's make it sure it's above the ground state, sorry. So these are all excited states. And all that means is that they're above the ground state. So if the first level is n equals 1 for the hydrogen atom, the second one is n equals 2, n equals 3, n equals 4, and so on and so forth until it gets to infinity. And the last level is the ionization state. So it's where it becomes ionized. Now, most people, and electrons can do this, most people when they walk up steps take one step at a time. So an electron could go from n equals 1 to n equals 2. It could go from n equals 2 to n equals 3, from 3 to 4, and so on and so forth. But if you're like me, and when you walk up a staircase and you take 3 steps at a time, an electron can also do that. So if it wants, it can go from n equals 1 all the way to n equals 4. Now, if if you're a human being, I guess like I am, and you're walking up the staircase, we have to go up from n equals 1, lift our leg up that step all the way to n equals 2, or if you're me, go from n equals 1 all the way, stretch that leg out to n equals 4. Now the weird thing about electrons is that they don't have to take that in-between step because, as Einstein said, they're quantized. So there is no in-between from n equals 1 to n equals 2. So what happens is an electron goes from n equals 1, it disappears and reappears at, say, n equals 3. There's no in-between process. It's either n equals 1 or any other n equals number or any other energy state. So it can't be anywhere in between. In order for an electron to go from n equals 1 to n equals 2, it has to gain energy. If we go back to the Bohr model of the atom, if the electron is close to the nucleus, its natural tendency is to be attracted towards the nucleus due to the electrostatic force. So it must absorb some energy or gain some energy to move farther away or to push it farther away in order to make it move away from the atom when it naturally wants to go towards the nucleus. So to go farther away from the nucleus, an electron must gain energy. Now it must gain a specific amount of energy. So if it's at n equals 1 and it goes to n equals 2, it has to gain that exact difference between n equals 1 and n equals 2. Or if it goes from n equals 1 to n equals 4, it has to gain that exact difference between n equals 1 and n equals 4. So the farther away the electron gets from the nucleus, the more energy it has due to the work being done on it. The way it gains energy is by absorbing a photon. And as we saw from earlier in the previous video, as I just mentioned, a photon, E equals hf, we can calculate that energy based on the color of the photon, or the frequency. So, also notice that when from n equals 1 to n equals 2, it takes a lot of energy to go from the ground state to n equals 2, and the farther away you get from the atom, it takes from the nucleus, it takes less and less energy to go to the next state. If a photon comes flying in, an electron will absorb that photon. That electron is going to disappear out of existence, and it's going to move up or reappear at that next energy level based on how much energy it gained. So a photon comes flying in, that electron absorbs that photon at n equals 1, and then it can reappear at a new energy state. And that's called a quantum leap, when that electron disappears out of existence and then reappears at a higher energy level. So quantum leap. So we'll say when an electron absorbs a photon, it disappears out of existence, and then reappears at a new energy level. Why don't we add a couple of things that we said earlier? So we can say the farther away an electron is from the nucleus, farther away it is from the nucleus, the more energy it has. And we can say due to work. And that work is the absorption of the photon. So if it absorbs a greater amount of energy, it'll be farther away from the ground state. Okay, we can also say that for an electron to move up or down in energy level, so if it's going to move up or down in energy level, it must absorb a photon to move up, or release a photon to move down. And we can say of that exact amount. Amount of energy. Actually, we should say of the change in energy. So the reason why these electrons aren't getting sucked into the nucleus due to the electrostatic force is because they're constantly absorbing photons, and they're absorbing energy that's pushing them farther away. Now what we could do is, let's look at the hydrogen atom. And here's a picture of the hydrogen atom at different energy levels. So when an electron goes from n equals 3 to n equals 2, it's going to release a photon in the form of red light. When it goes from 4 to 2, it releases a green photon. When it goes from 5 to 2, it releases a blue photon. 6 from 6 to 2, is a violet photon. And then any ones to the left of this, the Balmer series, notice when it goes from 2 to 1, 3 to 1, 4, 5, and 6, it's releasing ultraviolet light. And anything to the right of it, when it's going from 4 to 3, 5 to 3, 6 to 3, and so on and so forth, it's releasing an infrared photon, So the colors that we would see if we looked at a hydrogen gas tube through these glasses would just be red, green, blue, and violet. Let's draw a picture of what it looks like when an electron releases a photon. So we'll look at 3 different energy levels. N equals 3, N equals 2, and N equals 1. So let's say we have an electron at N equals 3. One possibility is that the electron can go from N equals 3, it'll disappear, and then reappear at N equals 2 and release a photon. That's a photon. Okay, it can also go from N equals 3 down to N equals 1 and release a photon of a different color. And then lastly, it can go from N equals 3 to N equals 2, and then also N equals 2 to N equals 1 and release a photon. Again, in a different color. Now, when we looked at the picture of my fluorescent light, what happens is once we turn on the electricity, so we flip the switch, an electron is going to go from one state, let's just say N equals 1, and then it'll go up to N equals 3, and then it naturally wants to go back down to its normal state, so that electricity gave it energy. Then it's going to go back down to its normal state. Oops, let's use the same color, It'll go back down to the normal state, and then it'll release a photon after it was excited. So it starts out at N equals 1, flip the switch, give it electricity, or turn on the electricity. It gains energy, So it starts at n equals 1, disappears, can reappear at n equals 3, it's excited, and then it's going to go back down to its normal states, and it'll release a photon. So that's how we see those specific colors of lights from the fluorescent light tube or gas tube. If we look in our Regents reference table, we can see that we have the energy levels of the hydrogen atom. Notice that ground state and the energy level is negative 13.60. Its units are electron volts. So negative 13.60 electron volts. And then as we get farther away, even though the numbers are getting smaller, they're getting less negative. So it's more energized the farther away. And then the highest state is when it's ionized, and that's at 0.00 electron volts. We can also look at Mercury, the ground state. Instead of n equals 1, we just call it A, and it's negative 10.38 electron volts. The next one is B, C, D, and so on, all the way up to J, in which it's ionized, and the energy there is 0.00 electron volts. So why don't we talk about the process on how to determine the color photon that's released from the light, or that's released from the electron, sorry. So how to determine the color of the photon. And really what we're trying to find is the frequency of the photon that's released. So the first thing that we want to do is we want to figure out what was that energy of that photon released. And to do that, we have to find the change in energy between the two energy levels. So the change of energy of the photon, I'm going to say it's the E high, and I'll explain what that is in a second, minus E low. So when we look at our reference table, if an electron goes from n equals 3 to n equals 2, the change in energy will be negative 1.51 electron volts minus negative 3.40 electron volts. Now if we get a problem and we say that electron goes from n equals 1 to n equals 3, and we want to find the color of light that it absorbed or the color of light that it'll release, we still want to do n equals 3 minus n equals 1. So E sub 3 minus E sub 1. So the E high is referring to the higher energy levels along the left side of this. Or for Mercury, the higher energy levels up the ladder. Okay, and then also the units in those tables are in electron volts. The next step is once we calculate the change in energy, all we want to do is convert from electron volts to joules. And that conversion is in the front page of our reference table, where we have 1 electron volt is 1.60 times 10 to the negative 19 joules. I guess we'll write it down for a reminder. 1 EV is 1.60 times 10 to the negative 19 joules. Okay, so once we know the energy in joules, we can now calculate the frequency of that photon. So we want to calculate, I feel like I spelled that wrong. Calculate frequency. And to calculate the frequency, we'll just use E photon is equal to HF. H is Planck's constant, F is the frequency. And then lastly, now that we have the frequency, we can finally match up that frequency in the electromagnetic spectrum to find the color. So match the frequency to the color in the E and M spectrum. So why don't we do one together, just so we have a better idea of how to follow all these steps. And we're going to do number 3 from the Bohr atom homework. So problem number 3. I have to take my glasses off. Sorry, I can't read it. Number 3. An electron in a hydrogen atom is excited to the n equals 6 energy level. Determine the energy of the photon released when the electron falls to the n equals 2 energy level. So for 3a, we want to find the energy of the photon. We'll say the change in energy. And it's going from 6 to 2. So it'll be E sub 6 minus E sub 2. We can look up the energy levels in our reference table. So it's going from E sub 6, negative 0.38 electron volts, minus negative 3.40 electron volts. Negative 0.38 electron volts, minus, don't forget that double negative, so minus negative 3.40 electron volts. We plug that in our calculators and we get positive 3.02 electron volts. So that's 3A. 3B, determine the frequency of the photon. In order to determine the frequency of the photon, we first have to go from electron volts to joules. So why don't we do that first? 3.02 electron volts. We want to get rid of electron volts, so 1 eV goes on the bottom. That's equal to 1.60 times 10 to the negative 19th joules on the top. Plug that in our calculators and we get 4.83 times 10 to the negative 19 joules. And now that we have the energy in joules, we can calculate the frequency. E photon is equal to HF. So F is E photon over H. Plug and chug, E photon is 4.83 times 10 to the negative 19 joules, all over H, which is Planck's constant, 6.63 times 10 to the negative 34 joules times seconds. We plug that in our calculators, and we get 7.29 times 10 to the 14th hertz. And that's the frequency of that photon. Okay, letter C. Determine the wavelength of the photon. So this is, why don't we skip letter C for now, and we'll go to letter D before we get to the wavelength. Okay, letter D says determine the color of light. Let's go to our reference table. The frequency was 7.29 times 10 to the 14th hertz. We'll look at our electromagnetic spectrum. Let's start with visible light first. And 7.29 times 10 to the 14th falls within the violet range. It is possible to get things outside of visible light, so don't think you can't get something that's not visible light, because you can. Letter D is violet. Okay, and then back to letter C, determine the wavelength of the photon. We have a couple of ways to do this. We could either do E photon is equal to hc over lambda, or we can do v, which is the speed of light in this case, is equal to lambda f. Why don't we just do the second one, v equals lambda f, get lambda by itself, lambda is v over f. Again, v is the speed of light in a vacuum, so 3.00 times 10 to the 8th meters per second, over the frequency, 7.29 times 10 to the 14th hertz. Plug and chug and we get a wavelength of 4.12 times 10 to the negative 7 meters. And that's it for this video. Thanks for watching. I hope you found it useful, and I'll see you next time. See ya!